Hey, good afternoon. My name is Aisha Kibase. I'll be discussing about the neural network and I'll be covering two topics in neural network, which is perceptron algorithm and as well as a deep neural network. In perceptron algorithm, I'll be discussing about its introduction and the gradient descent and the activation function which are used in the neural network. Whereas in deep neural network, I'll be discussing about the what is epochs, backtracking, early stopping, momentum, and dropout. And let's see how it goes. I hope that it goes very well. So let's get started about the presentation. Thanks. Hi again. So let's get started with the presentation of the neural networks. Uh, so as I said before, I'll be covering two topics, which is perceptron algorithm and the deep neural network. And in perceptron algorithm, I'll be covering these topics. And Precedent algorithm and deep neural networks are not very much they are not very much different from each other. Deep neural network is just like the extension of the perceptron algorithm. So what is neural network? Neural network is in computer networks or maybe in computer system we can call it as a the information which is being passed from one neurons to other neurons. Actually, this neural network is it's got inspired by the biological neural network. If you just see this image, this is a biological neural network where the input is being taken to through these dendrites and the information is being processed, and through this axon and axon terminal is being passed from one neuron to other neuron. So this biological neural network can be found in the human brain or in the human body or any animals, which it contains thousands of neural networks. So by this biological neural networks, the computer scientists got inspired by them, and they have created the neural network for in computers. And this is the similar like if you just compare the image between the neural network of this biological neural network and the computer neural network, there's not much difference. You see, this is the input which is being taken, the information is being processed, and then the information is being classified, or it's being predicted. So even if you just go through the presentation over here, you'll find more layers of the neural network. So and then neural network got very popular since 2005, and it's been widely used in deep learning. If you just look at back at the time, neural network got revealed in 1980s, but it did not got very famous as it got very attention in 2005. And since 2005, and since it is being used in deep learning for image classification, now the neural network is being widely used in image classification or maybe text classification, self-driving cars, or if you just consider about the Google uses only one camera, but at the night mode over here, it just classifies the object, and it makes the things very colorful at the night mode image. So these are the few examples of the neural network, and there are many big companies such as Google, Amazon uses neural network for what we'll say, for suggesting the items when the user buys through the new item over here, and Apple uses for face recognition and the face unlocking and locking over here. So these are the few applications which I'm saying you right now, and these are the examples of the neural network where the image is being classified by the neural network, such as this image is classified as a cat, and these are the images which neural network classify them as a train station, beach, golf, or baby. So these are the few examples. So let's go inside through them. What are the topics? Why? How it's being implemented? So talking about the perceptron algorithm, perceptron learning algorithm, also known as the neural network, and it's an algorithm which takes the input and classifies an output. I'll just show you an image over here. So as I said before, it got inspired by the biological neural network. At one neuron, it contains the input. At other part, it processes the information. At other neuron, it predicts or classifies the information over here. So similarly, the biological neural network, it takes the information, process the information, and classifies whether it is predicts whether it is an object or not. So perceptron algorithm contains four items, which is input, weights, bias, and output, and it's a supervised learning. Without supervised, it is not unsupervised learning, where we have to train the model or train the neural networks way so that it can predict or classify the object. So now speaking about terminology over here. This is the bias, this is the input. So neural networks contains three layers, which is known as the input layer, hidden layer, and output layer. So input layer is the layer which takes the input. Now computer just understands about the numbers. If you just give them the input directly as an image, it will not understand. So we have to make them in the form of the numbers or in the form of the matrix, so that the so that the computers can understand what type of input variable it is taking. And then this is known as the hidden layer. At the hidden layer, it classifies the object, that okay, what type of object it is being classified, so that okay, it does not make any mistake at the prediction or classification. So at the hidden layer, it takes the input, it takes the information over here, it calculates something, it happens something inside. For example, it goes for calculation, it classifies the object between them. And then after doing all the stuff, all the information processing in the hidden layer, it goes to the output layer, where shows the information, where it predicts the information that okay, this is the object or not, whether it is correct or not. So now if you talk about the mathematical terminology, which is y is equal to wx plus p. So y is nothing but the output, w is nothing but the weight over here. This all the uh, the line which are connecting between the neurons over here, this is known as the weights, and x is the output and b is the bias. Now you may be wondering a question that okay, why bias is being used. Bias is nothing but a constant, it is a constant variable which is used to avoid overfitting over here. Now if you just later in the session over here, if you just give an output over here, this if you give an input over here, the information is being processed at the hidden layer and the output is being given. But at cases it will not give a correct output, so we have to backtrack again, so that the weights over here adjust themselves, so that okay, it just classifies the object correctly over here. You will get to know later about how the weight is being adjusted accordingly. But for now, this is the perceptual algorithm. This is a simple neural network which I'm showing you right now, which contains input, output, weights, and bias. Now if you consider an example of the neural network, this is known as the perceptual algorithm, which is used for understanding the acceptance at the university. So if you just check about this graph over here, it contains about the grades and the test. So whenever if you go for a new admission at a university has some conditions over here, that you have to get at this test, you have to get some very good grades, only then we can accept at the university. So if you just check away, it is using binary classification, where it is classifying the two students, or maybe it is classifying that the students who got 9 marks and 9 marks, and he got very good marks in 9 as well as grades 9, then only he'll get accepted in the university. But then if you just consider over here, if you got test 4 and grades 2, then he'll not get accepted. So this is the formula which I'm using over here, which is classifying the object between these two items over here, between these two data over here. So this line is a polynomial expression, which is 2x1 plus x2 minus 18. So if you just go back to the formula, y is equal to wx plus p. So y is nothing but you just don't worry about the y, but w is nothing but 2. 2 is the weight which is classifying the image between them, and x1 is one output, x2 is another output, and minus 18 is the bias over here. So if you just check this image over here, you have around like n number of input over here, and this is the weight. So depending upon the formula, depending upon the polynomial expression which we are obtaining by the binary classification over here, this input it will take over here, depending upon the weight which is connected the neurons between them. For example, now x1 it can have two weight, so this two weight will go to this input layer, and in the hidden layer this graph will be present over here. So it will classify the data over here, whether this student will be accepted or not. Whenever this new image or the new data will be given, not the new image, I'm sorry, but the new data will be given, depending upon the weight and the data, this will classify the image over here, and at the output layer it will give whether yes or no. And the bias is used, for example over here it's given -1, but -18 will be used, so that it can classify, it will reduce the overfitting in the model. And at the output layer, this is the one. For example, 1 1, for example, if you're getting 1 1 or 1 0 0 0 0 1, the student will not be accepted, but at the 1 1 the student will be accepted over here. So let me explain you once again. At whenever a training will be given, the data which is present over here, the normally the data, the all the input will be given over here for the training, and here will be all the graph. This graph will be present over here at the hidden layer, and it will classify the object. It will classify the data between these two data by drawing a line between them. Now this line is nothing but a polynomial expression which we obtained by classification over here. Now for example, if any input will be given, for example x1 will be given and the weight is 2 over here, bias is -18, and x2 is contain only one input. So whenever the new input image will be given, depending upon the weight and the input, it will be adjusted accordingly, and the value will be checked over here, and it will give an output. It will predict that key, it will be yes or no. As simple as that. You don't have to worry a lot. This is a very simple representation, but at the later stage you will understand how the neural networks works very well. Now, gradient descent. Now every model in machine learning tends to make error. For example, in this example, it will make error. For example, over here, if you check over here, these three dot lines, it's coming at the acceptance part of the data. So the model is making an error. The model is making an error over here, and in order to reduce the error in the model over here, we are using gradient descent. So gradient descent is the reduction of the errors on training when the input is supplied to preset an algorithm. So if you just consider about this graph over here, you just see this is the initial weights. Now just for example, just consider about over here, this is the initial weights about the polynomial expression. But then when we have to reach at the global, we have to reach at the minimum state of the error so that the model does not make any error during classification and predicting over here. So this is the error. Now this is the polynomial expression. Now whenever a new data is given with a new weight over here, and during prediction, during this one, what we'll say, during training over here, the model at the initial weights, it will try to reduce the error. The line between over here, it will tend to make a line over here so that it does all the data over here should come over here at the rejection data, and all the accepted data should come at the accepted data during training. So this at the during training over here, it will make a minimum state of the error over here. And if it reach at the during after training after doing giving a training over here and adjusting the weight accordingly, these values will be changed over here when the input will be given, when the input will be supplied to the perceptron algorithm, and then after reaching to the minimum state, it will check again. It will come again over here and check that this error is higher than this error over here. So the model concludes that it has reached to the global minimum error, it has reached to the local minimum error, or it is also known as the local minima also. And after reaching over here, the model is all set, and whenever the input is given according to the weights, and the input is whenever like new input and the weights are given over here, the model will classify and predict over here. And let me remind you again, whenever a new input is given, the weights will not be adjusted, but at some cases the weights will be adjusted accordingly. For example, if the new input has given for example, a student got 10 out of 10 in test, he got 10, and in grades he got 10 over here, but then the model will classify that it is a no. So then there's a big problem in the model. We have to again evaluate the model again. So it contains two types, which is batch gradient descent and stochastic gradient descent over here. Batch gradient descent is nothing but it will check every values. For example, it will check every values over here, and then whenever it is classifying the object, whenever it is classifying the data between them, it will every data will just tell these values to come further where it is coming at the correct data points over here. For example, these data points will tell to come further to the line so that it can make least error over here, and it can predict and it can give you very good accuracy. So if you just consider about these data points, it will tell this line to come further, And if you just consider about these three data points over here, these three blue points, it will tell this line also to come further over here. And if you just consider about these blue points, it will tell the line to go further, so that okay, it will reduce, it will have the minimum minimum, what we say, the minimum, um, how can I say about that one, the minimum, it will, so that it can have the maximum points over here, and these points should have the maximum reward points, minimum reward points over here. So depending upon that one, the batch gradient descent will make accordingly. And if you consider about the stock hasting gradient descent over here, stock hasting gradient descent, these all points will tell to come further. For example, these 3 points over here, which I was telling about, these three red points and these three blue points over here, it will tell these lines to come further, so that okay, they have the minimum, what will say, maximum reward points, and these point will tell the line to go further, so that okay, they can settle over here, and depending upon that, the weight and the model and the bias will be adjusted accordingly. And let me remind you one thing: in neural networks, the value of the gradient descent should be between 0 and 1. For example, if you just consider about the other things, such as like for example, if you just consider about the mountain over here, if you want to reach to the minimum state, if you want to reach from the highest peak to the minimum peak over here, you will take the minimum point over here. So the value should be between 0 and 1. It should be continuous. If you just consider about the stress over here, it's not very it's discrete over here. So the model, like whenever you're giving training to the model over here, the errors which the model will be making over here whenever classifying, or maybe whenever the line is being drawn between the two data points during binary classification, the errors will tend to make more mistake than the errors that will make in continuous values. So discrete values are not very suitable for neural networks. We have to make the value of the gradient descent in continuous variables, so that the model can classify at which point the at which point it can it can classify properly over here. So the value should be between 0 and 1. And before I go on, I'll tell you one thing. Whenever the input is given and according to the weights I just stated, over here at the input layer, these values over here will give the probability over here. Depending upon the probability value at the output layer, it will predict or classify. So over here, the information will be processing over here. The information will be processed. It will predict over here at which part it is correct or wrong. So the value of the probability will be given. The input is given according to the weights are adjusted at the hidden layer. The information is being processed, and when the information is being processed and it goes from one hidden layer to other hidden layer or to output layer, the probability values are being passed. And if the information is being passed from one layer to other hidden layer, then the probability value is being passed, as well as it's telling other hidden layer to classify more, that okay, at which part it is making mistake, uh, at which part it is being classified properly, and it tends to reduce more and more, error also according to gradient descent. So now in order to make it continuous values, we have to use activation functions. So activation functions are being basically used so that we can keep the probability or the gradient descent value between 0 and 1. So there are three types of activation functions, which are softmax function, sigmoid function, tanh function, and ReLU function. So before I go on with the activation functions, there are some graphs and the formulas. So please remember the formulas and the graphs, because these activation functions will be extensively used before every hidden layer, so that uh, while doing gradient descent of the model at the hidden layer, to reduce the error at the hidden layer, these activation functions are being used, and it will give the probability value between 0 and 1. So let's find out. Um, Now this is the input image, where the inputs is being given and the weights are being adjusted accordingly over here. Now this is the hidden layer, and after every hidden layer, this activation function is being used. So activation function contains sigmoid, tanh, or maybe like a ReLU function over here, which we'll be discussing right now. And after activation function, the information will be classified or predicted. So now this is a sigmoid function. Please remember about the graph and the formulas over here, because these formulas and graphs will help you to predict or make to reduce the errors over here at the hidden, like at the hidden layers, because while programming we'll get to know at which function these data sets will be used. So sigmoid function is an activation function that is placed before every hidden layer, as I said before, where the probability value can be between 0 and 1. So if you just see over here, the if you just consider the activation function at the hidden layer, this at this activation function, this sigmoid function will be used. For example, for the data set that the user is using, so it will just classify. For example, now it's a S shaped over here. Now, if you just take the values over here, minus e set 1 plus 1 divided by 1 plus e to the power minus z. So minus z is nothing but whatever the probability value it is giving at the hidden layer, this value will be formulated over here, and accordingly this the s to the power to the x over here, the points will be classified over here. So this sigmoid function at over here, and at the sigmoid function over here, depending upon the value of z, this sigmoid function will be pointed accordingly, and these values will be given in the form of 0 and 1. And during that case, if the sigmoid function comes in the negative case, again it will revalidate and make it to positive case. So don't worry about that one. These are the third-party libraries which implement these functions over here. You don't have to worry. Now let's go to the next function, which is known as softmax function. Softmax function is basically used at every output layer. Actually, it is used every after every output layer, where it will classify. For example, if you give a cat, dog, or maybe uh, a rabbit image to classify for the neural networks. Just go back to this image. Now don't consider about this university part. Just consider about this dog, cat, and rabbit. So when the input is given as a dog over here, it will go to this part, and the weights are being adjusted accordingly. At the hidden layer, it will classify. Maybe there are many hidden layers over here, and then after every like the cats will be classified by drawing an outline over here, and at the activation function this will classify matlab, like it will just make it will give the probability between 0 and 1, and it will give the probability value that this is a cat over here, this is a dog, this is the rabbit over here, and it is being used widely used at the output layer. So you just see the image. If you see the graph over here, the softmax scores for the inputs of the particular Docker, it's increasing. For example, if you just consider 10 at the 10 images, if you feed 10 images, it's not making a very good score. But if you give more than 50 till up to 100 also, it will give more and more score of the soft math score. So just look at the formula. S to the power ii is equal to e to the power ii to the whole sum, to the summation sum of e to the power ij. For example, if I give the example of cat, dog, and rabbit. For example, if I take the image of the cat, the probability that it is making at the image over here, that probability value will be taken, and to the power e, to the power sum of the probability of all the hidden layers. For example, if you have one hidden layer for cat, one hidden layer for rabbit, depending on the probability values, it will calculate the image and will predict that this image is a cat or not. So it is why I repeat again, it is widely used at the output layer of the perceptron algorithm before, and then it will classify that it is a cat, dog, or rabbit. Now let's go to ReLU function over here. ReLU function is basically used in CNN, which is convolutional neural network. So it will only give the values between, only give the positive values over here, and it will not give any negative value. For example, if you just consider, if the probability value is between 0 to 100, or maybe minus 1 to 100, but it will not, if probability value came minus 1, that will not give the value, it will give 0 only. The ReLU function value will be 0. But if the value is between 0 to 100, whatever the value we're getting from the probability value we're getting from the hidden layer, depending upon that function over here, we'll get the values over here, we'll get the probability value between 0 and 1, and then is widely used at the hidden layer, so that it only just gives the probability value and the gradient descent value with the minimized error between 0 and 1. Now, this is the very important topic in neural networks, which is known as the cross entropy. Cross entropy is defined is nothing but how well the model have been trained. There is nothing but there are two formulas over here which is used for binary classification and data points which contains for the multi-class classification also. So cross entropy is nothing but how well the model have been trained. We can understand, we can know that how well the neural networks have been trained, how well the neural networks have been classified when the validation data is being given or when the test data is being given. So depending upon the value over here, we can understand that the neural networks have been perfectly trained or not. Yeah, so this is the binary classification value. For example, if you this y is nothing but the output value, log p is nothing but the probability value, and then 1 minus y is nothing but the output value of the other value over here. For example, if you just consider about this image, y is nothing but this output value, log p is the probability value, and 1 minus y is nothing but this value, this other value, and log 1 minus p is the probability of the other value over here. Depending upon that one, we can classify, we can just go know about the entropy over here. And then for multi-class classification, you don't have to worry. You can just do the summation of, for example, you have three different data points over here. So the yi and log pi for other for one data point, yj log pj for other data points, minus yz log pz for other data point. Depending upon that one, we can just calculate about the cross entropy, and less I'm making a note over here, less the value of entropy, the model is better. The more the value of entropy, the model is not better. So just me give an example over here. For example, look at these three values, these three blue points and these three red points over here. So whenever the probability, this output the output value which we are getting over here, and the probability which we are obtaining over here. So as I said before, now it is in the wrong point over here, which is on the other side of the data point, which is on the other side of the data point when classifying. So it will have the maximum big error point over here, maximum error point, which will have the maximum gradient descent point over here. So depending upon the, if you have the probability, if you have the larger the value of the gradient descent, is the more the value of the cross entropy. So this is not very good. So and we can, this can indicate that the model did not learn very well, and it will tend to overfit also. So coming point on deep neural network. So coming part to the deep neural network over here. Deep neural network is nothing but like it's an extension of the back propagation. It's an extension of the perceptron algorithm, which will go in depth about the neural network, and we can adjust the weights accordingly in deep neural network, and then how we can just classify, how we can make more better probability value at the output and predicting the object over here. So first topic is the back propagation. Back propagation is nothing but the backwards approach from the output layer to our input layer. So if you just consider an example, for example, one input of 1 2 3 4 5, for example 5 input value is being given. So the 5 input value are being fed to the neural network, and accordingly the hidden layer probability is given, and then the output layer predicts or classify. So at the end of the layer, we can know about the accuracy as well as the cross entropy of the object at every output layer, depending upon the activation function which we are using at every hidden layer and output layer over here. So now if we don't get very good accuracy, because at one point the model have trained, but we have to train it more better so that the weights as well as the accuracy of the neural networks can be increased. So every, for example, if it contains 100 data points, so we can just simply fit 100 data points to this 5 input layers. We have to first what we'll say fit 5 input values over here, and depending upon that one we'll get the accuracy at each output layer. And when we get the accuracy, now these values depending upon the weight values and the hidden probability of the hidden layer which we are obtaining over here, depending upon the accuracy, these model will again go back over here to the hidden layer, again to the input layer, and the weights of the when back propagating to the input layer again, so that it can take another 5 input, the weights of them are adjusted accordingly, and the activation function also,
It's 15
and
hours.
the activation function also will be very good, and the activation function, the value which will get at the gradient descent will be very good also. So again, when the input again when we get another 5 input layer, the values again, this hidden layer will be adjusted accordingly, and output layer we will get more value of the more better value of the accuracy and the cross entropy. And to get more better value of the accuracy and cross, again it will back propagate, and again it will take a more 5 input data values. So this is known as the back propagation over here. And I said before, this is the input layer, hidden layer, and output layer. To get more good value of accuracy and to decrease the value of the cross entropy so that the model can learn very well without overfitting, then we use back propagation. And when the input is key one, and when it is going through this all these hidden layers to the input layer, it is predicting over here. And when to increase the accuracy, to take another 5 input data points over here, again it will go back to the input layer. So these the traveling of input layer to output layer, and again output layer to input layer to adjust the weight and everything, is known as an epoch. Okay, now let's consider, now as I was saying before, what is like epoch over here. So epoch is nothing but increasing, adjusting the weights accordingly over here. So when traveling from one input layer to output layer, and again from output layer to input layer, this is known as a one epoch. So epoch is defined as a measure of the number of times of all of the training vectors that are used once to update the weights. So as I said before, it is epochs are used to update the weights over here, and epoch is uses back propagation method so that it can adjust the weights accordingly over here, and it can reduce the grain descent and improve the accuracy as well as the cross entropy over here. So this is an epoch over here. It's not much of a topic, it's just like a definition. So back propagation and epoch are just similar to each other, and it is widely like it can, you can just define how many epochs you want, like how many training, how many times you can just train the neural networks accordingly. For example, if you want to train the neural networks, if you want to adjust the weights, and if you want good accuracy and reduce the value, like have less value of the cross entropy, then you can use more number of epochs. But you have to remember that if you use more and more, if you put a high number of epochs, then it will go to overfitting. But if you put a less number of epochs, then you will undergo underfitting. Just we will just explain, we'll just go through in over early stopping over here. We'll understand the graph over here where the value of the epoch, the correct value of the epoch can be used, so that it can neither be in underfitting nor overfitting over here. So now in gradient descent over here, we have just check how the gradient descent is being used to minimize the errors over here. But here comes one problem over here. Now vanishing gradient descent over here, when like when the data points, or maybe when the model wants to reduce the errors over here, now in this graph it just comes over here at the local minimum, and it'll just find that it'll just check at every other points over here, and it'll just find that this at this point it makes the local minimum, like it is scored the minimum error, it scored the minimum error at the training point over here. So, but the grade at the vanishing gradient over here, the problem is that at the gradient descent, when the training is being done to a neural network over here, then this at this point over here, the changes at the error over here, when you're training with the epochs, or maybe when you're training the neural networks over here, the changes in the gradient is very small. It's very small, because and then if you just like training for like 1,000 epochs also, you not reach over here at the local minimum, if you not reach at the least error point, and then it will make the model will tend to make a mistake over here. So this problem is actually overcome by this momentum. Actually, momentum is nothing but to momentum concept is defined to overcome the problem of finding the exact local minimum in the gradient descent. So it will just for example, if you just consider at this data point over here, whenever you're just training the model over here, and in order to reduce the error, the model will just assume that it has reached a local minimum point over here, and it will not go further more than that. But if you just check by ourselves over here, this is the local minimum point. So this model of the neural network will just consider this gradient descent, let me this error point as the least error and not go further, and this one very good for the model. So the momentum is nothing but it overcomes the problem of finding the minimum gradient descent point, exact local minima in the gradient descent. So what this if you just consider about the terminology, if the data points or if the model is starting to just reduce the error over here, so it will just continue to decrease at the training will just continue to decrease the error over here after training. At exact point after coming over here, at this point coming over here, again it will go to this point over here, again it will go to this point, and then it will just continue to just error minimize the error over here, just continue after at that training will just continue to check at which point is the local minimum error. So if it just checks away this point will be the minimum error, but then if you just go over here, the model understand that okay, this part is much better than this point, and if you give the most training up till here over here, so at this point over here, maybe at this point, maybe like at this point, if you just consider about this point over here of the training over here, when the training is being finished, it will just check that okay, this is the local minimum point. So just consider about this mathematical function, and this step is nothing but I, like for example, if the model is being trained, at each step, like at each training is known as the step. For example, like now this is the training data, this is the model is being trained, now this is the step. Now if the training goes to this step, the error is being decreased, so this is nothing but the step. And if you just consider this point, at this point when the training reaches at this point and it has reduced the error till here, and when continue training, so it will reach this point. So at this step over here, it will just consider as this step n. Step n nothing but the starting step, and then beta is nothing but the constant, like we can just give the constant like between 0 and 1. So and then if it reaches if it reaches at this point at the step n plus 1 n plus 2 to n plus m, and when it reaches the local minimum, the model will go to n plus m plus 1. So it will just check that key this point is being the error is being reduced. So depending upon the value, it'll just check n minus 1, n minus 2, n minus 3. So depending how the values is being increased, depending upon the value, beta value is being also, the power is being increasing by 1. So at this point, the model will find that okay, this is the minimum local minimum point depending upon the number of the steps, and at step n minus 1, n minus 2, the model will recognize that okay, this is the model over here, and at step n plus 1, n plus 2, the model will be recognized. So this is the momentum, and momentum and vanishing gradient descent are not are very much different. Actually, momentum is the overcome of finding the local minima in the in the gradient descent graph over here when training the model, whereas vanishing gradient is nothing but very small changes in the gradient descent over here. It's like what we'll say, it's making very small changes in the error when training the model. So now if we just consider about the early stopping, early stopping is nothing but it's a predefined model in neural networks, where the neural networks, it have a feature in neural networks that it will just over, it will not go, the model will not overfit, actually it will not overfit, it will come at the exact point where the model have learned properly over here. So if you just consider, if as I said before, uh, if you just consider at this point, yeah, at the epochs over here, that k at the every input over here, that k it will just overfit, the model will overfit when the epoch value, like when the number of the epoch value is being increased. So if you consider at this point, when the epoch value, when you're giving training to the model over here, so the accuracy now, the model accuracy. So in order to increase the model as well as to decrease the cross entropy of the model, so during training we will consider about the epoch. So if you just consider about 100 epochs, maybe 200 epochs, we can just specify in the program over here. So depending upon the number of epochs that you're giving during training of the model, so this is the graph between the accuracy and the epoch. At very low epoch, you can just see that okay, the accuracy value is very low, but then when the accuracy, when the epoch value is being increased, you can see that the accuracy value is increasing. So at this stage it is known as underfitting, because at the training accuracy score and the testing accuracy score is not very much difference. There's not a very large value between them, there's no very large difference between them. So this is known as under training. Then if you just give at 100 epochs, maybe 200 epochs, then the model is not, according to this graph, the model is not very good. The model is not classify or predict properly. But then at this stage, it is very perfect. At this epoch over here, the model can classify or predict properly over here, and this part the training should be enough or should be done over here. And this at this epoch over here, this is the perfect fitting of the model over here. And whenever the new input or the new data is being given, then the model can classify. And further, if the for example, if the user, or maybe if the computer user, maybe the programmer can give 1,000 epoch, then the model can increase and it can lead to overfitting. There will be like huge differences. For example, if I go further, it will be like this value, and over here this will be this value. So if there will be like large values between them, so this is known as overfitting. At the case of overfitting, the model memorize it. It will not predict properly, but at memory it will memorize it, and whenever the new data is given, it will classify it, but it will not learn properly. Don't learn properly. That's the main problem over here. So this is known as the early stopping. So this is like, sorry, this is not known as early stopping. Early stopping is nothing but at this point over here, the model will not stop. It will not. The accuracy will not decrease. The cross entropy value will not decrease further than that one. Because after that one, if we increase the accuracy, if the training and testing accuracy will, so after overfitting, ये overfitting की बात है. So after overfitting, at this point over here, you can see the large difference between overfitting and underfitting over here. But early in the neural networks model, or when you're importing the third-party libraries, we have a feature called early stopping over here. Early stopping is nothing but it will avoid the model to go into overfitting. At this point over here, you will not find that you will not see that accuracy model is being increased, or the cross interview value is not decreased. At this is the way the early stopping will detect that the model have learned properly, and now it's a time to test the data. Maybe it can classify or predict the value whenever new data is given. At this epoch over here, it will stop training the model, and then it will avoid overfitting over here. So dropout is a very important feature in neural network. Dropout is defined as the weights of the neural network can be well distributed among all the nodes of the layer in the neural network. So just consider an example. Whenever a model is being, the dropout method is being used after training the model. So after training the model, when testing the model over here, whenever a new image or maybe a new data set is being given at this point over here, so this point will go to every node of the hidden layer, and from this point it will go to every node of the hidden layer. It will classify, or it will predict the object over here. So for example, if we give an image of a cat over here, so it will go to every node and it will make an outline. It will make a probability. For example, at this point it will make 0.5, at this point it will make 0.6, at this point it will make 0.7, at this point it will make 0.8, at this point it will make 0.2. So from every, these values are coming from every node of the nodes over here, from every value of the nodes over here. So this can lead to overfitting when testing the data over here, and at that point it will not create, or maybe it will not create or classify the image properly. For example, take 50% of cat, 50% of dog, or 50% of cat, 50% of rabbit. So this is not good. So dropout, now what feature can be used. It is very useful at this point, so it can just take only the respective nodes over here. So if you just consider this image, whenever I'm feeding a new data set, it'll take only this respective nodes where the cat image can be predicted, can make more probability over it. It'll just go to the respective node at the hidden layer or the output layer. So it will just take that node, it will send that image to that respective nodes over here, and from the respective it will give the maximum probability, and the output that will predict or classify properly without overfitting. So this is where dropout method can be used very effectively. So now for example, if I give the image of a rabbit over here, so it will go to respective nodes at the hidden layer. For example, go to these nodes, it will give the maximum probability, and from there it'll go to three nodes of this hidden layer that can make an outline, or maybe it can just classify. It will give a more maximum probability along with activation function with the minimization of the errors, and the output will predict or classify properly. So let me explain this part. maybe if you can understand, or if you don't understand, please pick me, please drop me a question, because this is a very important point at the dropout. Let me explain you again. Dropout is nothing but after training it is after training the model, when testing the model over here, whenever a respective data is being given to the network, only the selected nodes of the hidden layer of the model is being selected, so that it can give a maximum probability. It can give better accuracy, it can give better prediction, or classify, it can do better classification of the particular object. So at this point, dropout is very effective, and can be very, it can be used very good over here, and it can be used to, it is particularly used to avoid overfitting, and it is not used to go to every point, every uh, node of the hidden layer. Only this goes to the respective nodes of the hidden layer, so that where we can get the maximum probability. We can predict that at this image is a particular object without making any mistake. So just I'll just tell you that, just go through these sentences once, maybe you can understand better. So thank you very much. I hope you like my presentation. I don't know how I explained very well. This is my first time teaching in a video. This is my first time teaching in a presentation right now. So I hope that it goes very well. And thank you very much.